Hi, in this video, we will now take a look at what happens when our characteristic equation has real but equal roots. So we already talked about what happened in the distinct case, real and complex. But now we have the last case, which is the repeated roots. And the idea now is that we cannot say that there can only be one solution set, as we need to have a second solution. So how do we get this second solution? Well, we can use the Abel's theorem to help us. So what does Abel's theorem tell us? Abel's theorem tells us that the second solution and the first solution must satisfy the WSQ, and the formula must be this. Okay, so we now know that y1 is known. So we want to know y2 now. So by Abel's theorem, we find that the WSQ, which is this determinant, must equals to this. And we already know how to do this, right? Because e to minus integral of pt is, you know what's pt, so this whole thing is known. So this whole thing is known, and the c need to be non-zero in order for this to form a fundamental solution. So we can just set c to be 1 without any loss of generality. And because of that, we see that y1 times y2 prime minus y2 times y1 prime must be this. And this reduces the question to a first order ODE, because we know this, we know y1 prime, we just don't know y2. So these are unknowns. We also know what is this. This allows us to create a first order linear differential equation, and from here we'll know how to solve it. So for example, we have this. We know that e to the power minus 2t will be a solution. Then we just use this equation over here, and this allows us to cancel e minus 2t, and with that we arrive to this new ODE. So this we can use the integrating factor formula, and this gives us x2 equals to te minus 2t plus ce minus 2t. But e minus 2t, well, that's one of the solution already. So this part is not, we can ignore this part, and this will form our basic, like the solution. And then you can also just check that this really solves the equation, and the WSQ between the x1 and the x2 now is non-zero. So in general, when we have repeated roots, we can always write the equation as the following. And in general, if you just solve it generally, we can use Abel's theorem to help us figure out that y2 will always be TERT. So it's like TY1. So the fundamental set of solution is y1 and ERT, and y2, which is TERT, which is TY1. Now that's a good example of when the equation has real coefficients. But now what happens if your coefficient is non-constant? So these are the non-constant coefficients. We are given that you know already one solution. So how do we find the second solution? Is, well, we convert it to standard form first, and again we use Abel's theorem to tell us what the WSQ must be. So in that case, then we now can solve this first order ODE to get that y2 equals to 2 over 3 e half. And from that, our general solution is c1 e minus 1 plus c2 e t half. So you can see how we use the method of Abel's theorem to help us solve for this repeated roots scenario. And with that idea, with that technique, now we are able to apply it to other type of equations, such as having non-constant coefficients. So this is the first method of doing it. The next method of doing it is known as the reduction of order. It is something similar as what we want now is to make our second order formula into order ODE into a first order ODE. And how are we going to do that? Okay, so we just want to find a second solution, and what we need is we just let y equals to a function in terms of t times y1. Okay, then when we differentiate twice, once we get this, and differentiate twice we get this, and we substitute them into equation 27 over here, and we collect the terms. This allows us to form this equation. But we already know y1 is a solution. So actually this and this cancels out because they will equals to 0. Right, this will equals to 0. So in the end, we are only left with this portion over here. And this reduction of order, despite its appearance being a second order ODE, we can just let u equals to v prime. Then this is actually just u prime and this is just u. So this becomes a separable equation and we can easily find the answer to it. So we should just give an example and you'll better understand this method of reduction of order. So how did people think of this is we just gathered the inspiration from using Abel's theorem. We just see that it is actually y2 equals to t times y1. In this case, it's just y2 equals to some function times y1. Also, you see this t cubed minus 3 over 2, this t half. So people just like decided that it could be just a function in terms of t times y1, which is very natural because like imagine you have equal roots. So it's like one root is this, the other root is just some function that has multiplied with this equal root. So we just see, okay, so given that y1 is this solution, then want to find the fundamental set of solution, we just let y equals to some function times t minus 1. Then the prime is this, the double prime is this. Substitute into 31 and we get this formula. With that formula now, we just let w equals to the v prime. It will be reduced to this first order ODE. We solve for w easily, which is ct half. Then v will just equals, so we know that v equals to v prime equals to w. So we already know w, we just need to integrate to get v, so this is the answer. And it follows that y equals to v times t minus 1 is this. This part you can ignore because it is a multiple of y1. And we just see that y2 will just equals to t half. We just need to check the one strand to be non-zero, and we see that we arrive at the same formula as when we use Abel's theorem. So that's it for the procedure. Very simple, very straightforward. You can practice more using the textbook, and I'll catch you again in the next video. See you.